a lost world of giants 60 million years old, ruled by a slithering monarch, unbelievable size. It sounds like fantasy. It's the biggest of its kind ever to live. This is Titanoboa.
We were wrong about Titanoboa. What scientists just discovered is terrifying. For decades, the story of Titanoboa seemed complete. Scientists had found it, named it, measured it, and declared it the undisputed heavyweight champion of prehistoric predators. News headlines called it a super anaconda, a living nightmare from the deep past. Museums built life-size models of it. Documentaries gave it the same cinematic treatment as the T-Rex. We thought we understood this creature. We thought we had it figured out. But a series of discoveries, from a coal mine in Colombia, from a lignite pit in western India, and from painstaking laboratory work by researchers at institutions including the Florida Museum of Natural History and the Indian Institute of Technology Roorkee, have quietly dismantled a version of Titanoboa that the world fell in love with. The truth that has emerged is stranger, more sobering, and in many ways, far more terrifying than the original myth, the discovery that changed everything. The story begins in the Serpent coal mine in northern Colombia, one of the largest open-pit mines on Earth. In 2009, a team of scientists co-led by Jonathan Block of the Florida Museum of Natural History and Carlos Jaramillo of the Smithsonian Tropical Research Institute pulled something extraordinary out of the ancient rock. Researchers have been excavating this site for years, primarily searching for fossilized plant material from the oldest known rainforest in the Americas. What they found instead was a bone so large that it defied immediate classification. A fragment of vertebrae, initially suspected belonged to a crocodile, turned out to be something else entirely. When the full analysis came back, the scientific world had a new name to reckon with: Titanoboa ceruginoensis. Using the ratio between vertebral size and body length as seen in existing snake species, researchers Jason Head of the University of Toronto, Mississauga, and David Polly of Indiana University estimated that this snake had reached approximately 13 meters, around 42 to 45 feet, in length. Its weight was estimated at well over 1,000 kilograms, roughly the weight of a small car. In total, fossils from 28 individual specimens were eventually recovered from the site, painting a picture of a creature that had not merely existed, but dominated. Titanoboa lived during the Paleocene epoch, approximately 58 to 60 million years ago, an ecological vacuum left behind by the mass extinction that wiped out the non-avian dinosaurs. With the giants gone, reptiles surged, and no reptile surged harder than Titanoboa, the myth we built around it. The problem was never the discovery itself. The problem was the story we attached to it. Because scientists had found vertebrae and ribs before they found a skull, early descriptions of Titanoboa were necessarily incomplete. Researchers and science communicators filled the gaps with the most obvious comparison available: the modern anaconda. The result was a popular image of Titanoboa as essentially a scaled-up version of South America's largest living snake, a colossal constrictor prowling the ancient forest, ambushing prey on land, squeezing everything it encountered into submission. That image spread rapidly. It was simple, dramatic, and deeply wrong. The first problem with this narrative was physical. When researchers began constructing detailed biomechanical models of Titanoboa's body, they ran into an immediate obstacle: gravity. A snake weighing over 1,000 kilograms and measuring nearly 45 feet cannot effectively move across dry land. The physics of blood pressure alone would have created serious cardiovascular stress if Titanoboa attempted any prolonged terrestrial activity, as the heart would need to pump blood against gravity across an enormous vertical range. The creature's own mass would have worked against it on solid ground. This was not a land predator in any meaningful sense. It was something else. The vertebrae themselves told a different story. The wide, robust ribs suggested exceptional lung capacity, well suited to extended submersion. The bone structure of the spine indicated an animal built to handle the compressive forces of deep water, not the dry friction of a forest floor. Everything about Titanoboa's skeleton pointed to a life spent almost entirely in the water, in the wide, slow-moving rivers and swampy basins of the ancient Serpent ecosystem. What the skull finally revealed. For years, the skull of Titanoboa remained frustratingly out of reach. Snake skulls are composed of numerous delicate bones held together by soft tissue ligaments. which means they almost never survived the fossilization process intact. Then researchers found one, or at least enough fragments of one to fundamentally rewrite the creature's biography. When Jonathan Block and his colleagues analyzed the skull material, what they found surprised them. The skull measured approximately 16 inches, a size that implied a body length toward the upper end of previous estimates, potentially reaching 47 feet. But the more important revelation was in the teeth and jaw structure. The skull of Titanoboa showed features characteristic of fish-eating snakes: weakly fused, recurved teeth designed to grip slippery prey rather than to crush it, a shallow jaw joint adapted to seizing aquatic animals, and a palate arrangement consistent with piscivorous diet. This was an animal whose primary prey was fish. The ancient Saragen ecosystem was rich in exactly what Titanoboa needed: large lungfish, osteoglossomorphs, and other substantial bony fish that thrive in the warm, shallow river systems of Paleocene Colombia. The jaw's flexible construction, with bones connected by elastic ligaments rather than rigid fusion, allowed the mouth to expand dramatically to accommodate large prey. Combined with the sensory adaptations researchers have identified, large nasal structures for detecting chemical trails in the water, and receptors sensitive to vibrations generated by moving fish, Titanoboa emerges not as a land-stalking constrictor, but as a masterfully adapted underwater ambush hunter. It likely rested motionless at the river bottom, invisible in the murk, waiting for the tremors of an approaching fish before striking with sudden, explosive force. It also shared its world with prey that wasn't fish. A small crocodile from the same formation, named Sarageniscus improcerus and described by researchers at the Florida Museum, grew to only about 6 to 7 feet in length, making it a manageable target for a 45-foot snake. Fossil turtles from the site, including the enormous Carbonomys cofrinii, which had a shell stretching nearly 6 feet across, provided further evidence of the diverse ecosystem Titanoboa inhabited. The evidence suggests Titanoboa was an opportunistic apex predator, primarily a fish hunter, but fully capable of targeting crocodilians and other large animals when the opportunity arose. A rival emerges: the discovery of Vasuki indicus. For 15 years, Titanoboa held its title unchallenged. That changed in April 2024, when paleontologist Debajit Dutta and Sunil Bajpai of the Indian Institute of Technology, Roorkee, published a paper in the journal Scientific Reports describing something remarkable. From the Penandro lignite mine in Kutch, Gujarat, in western India, they recovered 27 well-preserved fossil vertebrae belonging to a previously unknown species of giant snake. The researchers named it Vasuki indicus, after the mythical serpent depicted coiled around the neck of the Hindu deity Shiva. The numbers were staggering. By scaling the verbal dimensions against those of known living and extinct snake species, Dutta and Bajpai estimated that Vasuki indicus had reached somewhere between 10.9 and 15.2 meters in length, roughly 36 to 50 feet. The upper end of that range would match or potentially exceed Titanoboa. The authors were appropriately cautious, noting that estimates from incomplete vertebral material should be treated carefully without a full skeleton to confirm them. But even at the conservative lower bound, Vasuki indicus was clearly one of the largest snakes to have ever lived. What makes the discovery particularly significant scientifically is that Vasuki indicus was not related to Titanoboa at all. Titanoboa belongs to the Boidae family. It is a true boa. Vasuki indicus belonged to the Madsoidae, an extinct snake family with a lineage stretching back over 100 million years to the late Cretaceous, and which spread across Africa, Europe, India, and South America during its long existence. These were two completely separate evolutionary branches that independently arrived at roughly the same colossal size on opposite sides of the planet, tens of millions of years apart. Scientists call this convergent evolution, and its appearance here suggests that the environmental conditions of the ancient world were so powerful that they drove unrelated lineages toward the same biological solution. Vasuki was also behaviorally different from Titanoboa. Based on the cylindrical, thick-bodied form indicated by its vertebrae, Dutta and Bajpai believe it was a slow-moving constrictor, more analogous to a modern anaconda behavior, that relied on ambush and raw constricting power rather than the aquatic speed strike strategy suggested for Titanoboa. It lived during the Middle Eocene, approximately 47 million years ago, when India was in the process of colliding with Asia. The researchers proposed that the intercontinental land routes created by this collision may have enabled Vasiki's lineage to disperse from India into North Africa through southern Eurasia, ultimately giving rise to other large matsoid forms found on that continent. The engine behind the giants. Both Titanoboa and Vasiki indicus point to the same underlying mechanism: heat. Snakes are ectotherms, meaning their body temperature is governed by the environment around them. The warmer the world, the faster their metabolism runs, the more they can eat, and the larger they can grow. Research on the climate of the Paleocene and Eocene epochs indicates that tropical temperatures during these periods were extraordinary, with some estimates suggesting average annual temperatures in equatorial regions reaching around 30 to 34 degrees Celsius, significantly warmer than modern tropical rainforests. As Jason had noted in the original Smithsonian description of Titanoboa, the snake's size itself serves as a kind of paleothermometer. An ectotherm of that mass requires a specific sustained temperature range to maintain its metabolism, allowing researchers to backfill the ancient climate data from the bones alone. Dutta and Bajpai made a similar observation about Vasiki. The warm temperatures of the Eocene, combined with the abundant prey available in Gujarat's ancient coastal ecosystem, created conditions that allow cold-blooded animals to sustain enormous metabolic demands. There's also a thermodynamic advantage to being large. A bigger body retains heat for longer, buffering against temperature drops at night or during cooler seasons. This thermal inertia likely allowed both Titanoboa and Vasiki to remain active and effective predators across a broader range of daily conditions than their smaller relatives. Conversely, this dependence on external heat was also their greatest vulnerability. As global temperatures began declining after the Eocene optimum, the planet's thermostat slowly turned down. For a cold-blooded animal requiring sustained warmth to support a 1,000-kilogram body, even a modest multi-degree drop in average annual temperature can be catastrophic. The metabolic engine slows, hunting becomes less efficient, reproduction falters, and the population collapses. Smaller snakes, requiring far less energy to sustain themselves, could survive the transition. The giants could not. The warning hidden in the bones. There is an uncomfortable irony embedded in the story of Titanoboa. We discovered it while mining coal at Sergin, and we discovered Vasiki while mining lignite in Gujarat. In both cases, we were extracting fossil fuels laid down in the ancient world to power the modern one. The same combustion that is driving contemporary climate change is what funded the excavations that revealed these creatures to us. And those creatures are, in a very direct sense, a record of what a significantly warmer Earth looks like biologically. As Debajit Dutta noted in commentary following the Vasiki publication, current temperatures are rising too quickly for snakes to evolve to giant sizes on any relevant timescale. Evolution does not move at the pace of industrial carbon emissions, but a more fundamental point stands. The conditions that produced Titanoboa and Vasiki were not random. They were the predictable biological response of cold-blooded life to a hot planet. The fossil record documents that when the Earth's thermostat climbs far enough, reptile size follows. We are not on a trajectory to produce new Titanoboas in our lifetimes, but we are running an experiment with a global climate that these ancient bones give us a preview of, one that took millions of years to play out the first time, and ended with the disappearance of every giant it produced. The bones in the rock of Sergin and Kutch are not just a record of extraordinary animals. They are a letter from a warmer Earth. We have now decoded enough of it to understand what it says. The question that remains is what we choose to do with that information. What makes Titanoboa's story so enduring is that it refuses to stay in the past. Every time researchers return to the Sergin Formation, new fossils emerge that complicate and enrich the picture. The original description of Titanoboa in 2009 identified the creature from vertebrae alone. The subsequent discovery of skull fragments required a full reassessment of its diet and behavior. New studies of the Sergin ecosystem have continued layering in detail the ancient turtles, the small crocodilians, the fossilized plant material from what is now recognized as the oldest known neotropical rainforest in the Americas. Each piece changes how we understand the whole. And with Vasiki indicus now added to the equation, paleontologists are beginning to reconceptualize the Eocene not as a period of isolated biological curiosities, but as a genuine age of giant reptiles, one that unfolded across continents simultaneously under the pressure of a shared global climate. There's also something worth sitting with in the sheer human experience of this discovery. The miners at Serpent went to work every day extracting coal from rock that happened to contain the fossilized remains of the largest predator to walk the post-dinosaur Earth. The workers at the Penandro mine in Gujarat did the same, unknowingly digging around the vertebrae of a rival titan. These creatures were hidden in plain sight, buried under the daily labor of industry, waiting for someone to look closely enough to recognize what they were looking at. It is a reminder that the fossil record is not an archive we have fully cataloged. It is an ongoing excavation, and every layer peeled back has the potential to change the narrative again. The version of Titanoboa that science now presents to us is more constrained, more specialized, and more ecologically precise than the movie monster image that made headlines in 2009. It was not a roaming predator of the forest floor. It was a river hunter of extraordinary patience and power, shaped by tens of millions of years of evolution into the perfect ambush machine for a specific type of warm, fish-filled ancient waterway. It was a product of its world, and when that world ended, so did it. That is not a diminishment of what it was. If anything, it makes the creature more remarkable. Titanoboa did not persist because it was indestructible. It thrived because it was perfectly matched to its environment, and it disappeared when that match was broken. The lesson written in its bones applies far beyond paleontology.